To understand linear algebra at the university level, students often turn to Hoffman and Kunze. The text builds the subject from the ground up, relying on strict logical proofs rather than computational shortcuts. Most introductory courses teach matrix operations using standard real numbers, but a mathematician asks a different question. What is the absolute minimum set of rules required for matrix mechanics to hold together? We assume that to do meaningful math, we need the ability to add, subtract, multiply, and divide. We don't. When we drop the requirement for division, we leave the mathematical construct known as a field. We enter a stricter, more restricted space, where matrices still operate perfectly. To see the actual logical scaffolding of linear algebra, we have to abandon the comfort of standard arithmetic. We have to enter the commutative ring. Moving from a field to a ring is a required step in mathematical maturity. It forces us to prove theorems without relying on familiar habits. Without division, we cannot rely on fractions to balance equations. We are forced to build our proofs using only the foundational behavior of addition and multiplication. In this constrained environment, the determinant of a matrix ceases to be a messy combinatoric formula to memorize. Instead, it emerges as a strict, unique function locked into place by exactly 3 absolute axioms. By stripping away the crutch of scalar division, we expose the unshakable foundation of matrix theory. A mathematical field, like the set of real numbers, is defined by 9 properties governing addition and multiplication. This list displays those axioms, and the 8th property is the multiplicative inverse. For every non-zero element x, there is an inverse that multiplies with it to equal 1. This is the exact mechanism that makes division possible. We strike it from the record. What survives is a set of elements forming a commutative group under addition, where multiplication remains associative and distributive. We establish 2 final constraints. Multiplication must be commutative, meaning x times y equals y times x, and the scalar value of 1 must exist. We now have a commutative ring with identity. The set of all integers operates exactly this way. The same is true for polynomials. You can add them and multiply them, but dividing them does not guarantee your answer remains an integer or a polynomial. Matrix operations, scaling, adding, and multiplying rows by columns, require only addition and multiplication. Matrix theory survives the transition to the ring. The determinant maps an n by n matrix to a single scalar element. Axiom 1 requires this function to be n-linear, operating linearly on one row while holding others fixed. Axiom 2 dictates it is alternating. An identical adjacent row evaluates to 0. Because the function is alternating, swapping any 2 adjacent rows multiplies the final output by -1. Axiom 3 is normalization. The determinant of the identity matrix evaluates to exactly 1. These 3 rules create a rigid logical framework. If it satisfies n-linearity, if it is alternating and maps identity to 1, it forces a single, unique solution for any square matrix. This animated expansion derives the 2-by-2 case. We start by expressing the 2 matrix rows as linear combinations of the standard basis vectors. Applying the n-linear axiom allows us to distribute the function, expanding the equation into 4 distinct terms. The alternating axiom demands that any determinant evaluating identical adjacent rows equals 0. The 2 terms with duplicate basis vectors immediately drop out. The remaining 2 terms contain the basis vectors in opposite orders. By swapping the rows in one term, we flip its sign to negative. Then, the normalization axiom converts the basis determinants into 1s. The result is A11 times A22 minus A12 times A21. The standard formula for a 2-by-2 determinant is not an invention. It is a direct consequence of the axioms. The commutative ring and the determinant function share a unified logical architecture. We derived a precise matrix property, relying exclusively on addition and multiplication. Division is an operational convenience. It is not required to establish the structure of linear algebra. The determinant is an algebraic necessity, defined strictly by the requirements of linearity and symmetry. This axiomatic method scales effortlessly. It provides the mathematical proof that for matrices of any dimension, exactly one determinant function exists. By setting aside rote formulas and returning to first principles, we uncover the inescapable logical patterns governing matrix theory.